gives me great pleasure to introduce Melonee and Fergs here. They've been members of our club for a while, and they are doing a great robot. I sometimes will make the analogy to the computer industry where we had the mainframe era. We are clearly well into the mini computer era. It's an exciting time. So I'm going to hand it over to Melonee.
Thank you. Everyone can hear me. I'm Melonee Wise. I'm the CEO of Unbounded Robotics. Over here to my right is Michael Ferguson, our CTO. And so back in January of this year when we spun out, a lot of you came running up to me and you were like, Melonee, what are you building? Come on, tell me. And half of you asked me if we were building ROC. And no matter how desperately I wanted to give that to you, we're not there yet. I hate to break it to you. So the question that people really constantly are asking is the personal robotics revolution here yet? And what I'm trying to do here tonight is kind of frame the importance of what we're trying to do at our company with this robot and how it fits into the greater vision of robotics and the robotics revolution, specifically for personal robots. After I give my talk, I'll answer a couple of questions, and then Mike is going to give a more technical demo showing some of the software on the robot. So in the 1920s is when robot first actually became a word, a commonly used word, and it was actually used in a Czech play. And in that play, actually, these mechanized beings took over the world, like all robots do, it seems. And then, only a short 6 years later, Fritz Lang actually made a movie called Metropolis, which is considered one of the first robot movies. And again, the eventual demise of the human race at the feet of robots. And so here we are in the 1920s. A robot actually hasn't even been built yet, and we're already predicting that they're going to take over the world. And that's kind of like, Henry Ford, he just puts the Model T on the market, and then Back to the Future comes out and it's like, yeah, but we're going, we don't need roads. And so you're like, well, come on, Henry, where's your autonomous horseless carriage? And so that's kind of some of the pressure that's been put on robotics, even as far back as the 1920s. We don't even have robots yet. So in 1939, what is considered maybe one of the first robots, and what if you ask people before 1950 what a robot was, they refer to Electro. Electro was actually just a mechanism, and it could do 26 unique tasks. And what was really cool about it is it had a whole bunch of vacuum tubes and things like that, and the operator would speak into a can in a kind of a Morse code pattern, and he'd be like, okay, Electro, let's go. And if there were 3 things, the robot would walk. If there were 3, then 5, then 2, the robot would smoke. Because, that's what all robots need to do. And so those 26 actions were really cool, but it again set expectations in the bar really high. And we don't even really have a robot yet, So then, 1942, still no robots, but Asimov has already made rules for us. It's pretty rough. Lots is already, the field hasn't even started. Okay, so then, 1948, our first robot, bio-inspired robots. So, Gray Walters was obvious in Great Britain, and he made what was called the first turbo robot. And he actually made a pair of them, Elmer and Elise, and they could drive around and react to their environment, and it was all the rage. Dude, I wish I could have done this. He actually made some very interesting and complex contraptions all the way back to 1948, and they could react to their environment very well, so it was pretty cool. But then 1954 came, and it was awesome. So the unit arrived, and we suddenly jumped from bio-inspired turtle robot that doesn't do much. 1954, the unit is So this is a programmed particle transfer device, which is really cool because they didn't even start calling these robots even then. And this robot actually took 7 years to finally ended up as the first robot in a GM manufacturing plant. It would actually pull very hot things out of press and then cool them down. And what's really cool about the unit is that it actually didn't have a computer. It was, all the programming was done on metal tapes, like metal drums, and it was completely pre-recorded, and you would put it in there, and you would run the operation, and just do that forever. And so, you still, at this point, you don't have computers really controlling robots. And then in 1966, and the first thing that happens is Ford pneumatics to homogeneous transform. Groundbreaking. It enables robots and computers to finally come together. The math is there to finally do interesting things with robot arms. And so the Rancho arm is the first computer-controlled arm. It's still not electric, it's fully developed arm. And then several years later, the Stanford arm comes out, and it's the first fully electric computer-controlled arm. And that's groundbreaking. And that happens all through the course of the 60s. But unfortunately, so we're barely moving our arms in robotics, and how is kicking our butt, you know? And again, here we are, as roboticists. We've barely got robots, and we've got, robots taking over the world, people in space. I mean, they're not even on Earth anymore, they're in space. And then in 1970, the dawn of modern-age robotics. Shaky, which was created in the Stanford Stanford Research International. It wasn't going to be called Stanford Research. It started off with that. Yeah, it started off with that, and then it became SRI International. But what's really cool is this robot actually could drive around autonomously, and the way it would actually execute its programs is it would collect data locally on the machine, and then it would use radio transmission to transmit it back to 3 servers. And when you think about this, in the 1970s, people were already doing wireless communication between this robot to do off-board execution. And what's interesting is she actually took about an hour to drive 2 meters across the room. So we're not going groundbreaking speeds here. At that same time, while people were working on autonomous mobile robots, people were also working on autonomous manipulation robots. So Freddy and Freddy 2 were 2 manipulation robots that could identify blocks, produce about and stack them. So here we've got the 2 parts of personal robotics kind of sitting out there across the United States in different labs, and people are working on autonomous mobile robots and autonomous manipulation. And there we are again. So we barely have arms and legs, and we've got some clear view. So again, at every turn, robotics is constantly set back by undue expectations. So then in 1979, the Stanford card came, and Stanford card was really interesting because it did all the processing on board. It actually was able to go across an entire room full of obstacles like you see here by itself. It may have taken 8 hours to do it, but that was pretty high tech for the time. Suddenly you had its only autonomous agent. You could let it loose in the room and it would do behavior monitored and probably the people sitting there worrying. But it was the first step in truly autonomous behaviors. So then the 1980s came, and everyone went in every direction possible. It was truly a birth of everyone doing anything they could for robots to do phenomenal. And it was very limited to people with lots of financing and money to do interesting robotics. And a lot of people worked on walking robots that could play instruments, robots that could drive around autonomously, and we saw a lot of movement in industrial robots because they had very nice conditions. Everything was kind of green environment. All you first stab at the consumer robot, so Hero. Hero actually was released in the 1980s, and it was supposed to be, your personal robot. Come on, guys, Ferguson, it's here. In the 90s, we saw a lot of evolution of robotic designs. So the IO, the Unbounded Robots, and we also saw that robotics was starting to become more into the consumer space and more into what you might call mainstream. So it first started in the 90s. It's hard to believe that's when it started, but it actually started in the 90s. And it's taken this long to become as vibrant as it is today with so many competitors. And so you're probably thinking like, wow, the founders of this company must have had like unbelievable resources and access to robots, and then there's me, and that's my first robot actually. It's like two pieces of plywood stuck together with some motors. Then that's my second robot, and then hot deck is with Derek, one of our other robots worked on, and these are not jaw-dropping robots. These are not oh man, these founders really have all these access to all these interesting robots. No, this is one of the problems with playing robots, even as late as 2004, is that there really hasn't been access to hardware to enable young people like myself, or like I was then, to do interesting things in robotics. And in 2007, I actually went to go work for the little garage, and we started working on ROS. And ROS is what kind of catapulted robotics development from people doing everything that I showed in the 1980s and the 1990s and not talking to each other to something talking to each other. So open source middleware enabled programs that used to run on one robot to run on many, many robots. All the robots shown in this video actually are running the same software, which is very empowering. And then in 2010, Little Garage released the Pier 2. And the Pier 2 kind of showed something interesting about having a platform for robots. So there's today 43 Pier 2s in the world. They're spread out in about 39 institutions. Some people have two. And what it enabled is collaboration on a whole other level. When you have robots that are not the same, it's very hard, even when you have a common software infrastructure, to have common applications that can be run on those robots. It's the same as phones, it's the same as computers. You have to have a bridge to start developing applications. And the Pier 2 was kind of the robot that made that bridge, combined with across the software platform. And so, when we compared Pier 2, there were a lot of other mobile manipulation platforms that came out around that same time. And the difference between them and Pier 2 is there's only one of them. And they're pretty big. Most of these robots cost about $300,000 to $400,000, just like the Pier 2. But the difference between these and Pier 2 is, like I said, there's only one of them. And it was very hard to collaborate among these robots and help advance state-of-the-art robotics. And then in 2011, Mike started, you can see that Ross enabled people to do interesting things. Mike was able to do all sorts of interesting things with hardware that Derek and I weren't able to do in 2004 because the software was there to enable him to prototype and do things faster and iterate hardware easier. And so in 2011, myself and a coworker actually worked on a project called Turtlebot to try and bring the cost bar down for enabling people to do more interesting things with mobile robotics. But the big feedback we got is, well, all we can do is drive around, and that's not very interesting because we can't actually interact with the real world. So when we spun off from Brew Robotics company, we wanted to change that. We wanted to enable people to have access to robotic platforms at unheard of price, $35,000, to really enable a large amount of people to have access to a single platform and change the landscape of robotics. And we see this platform as not only something that can be used by universities and researchers and corporate labs, but also as something that can go out and do real work in our businesses. And that's kind of our vision for our company and just advancing the state of our robotics in general. So I will video and ask if you guys have any questions, and then I can quickly step through some of the components of the robot, and then Mike's going to do more technical work. So, yeah.
What did you say the cost of this was?
And the question was, what is the cost? The cost is $35,000 for the base model.
What's the difference with Baxter?
The question is, what is the difference between this robot and Baxter? There's several differences between this robot and Baxter. Baxter is not a mobile robot, this robot is, so it can drive around. It also has the ability to have a telescoping torso, so it can lift itself up and down. It has a single arm as compared to Baxter, but this robot is also an integrated platform, so it has a complete vision solution. Baxter only has webcams and its grippers, whereas this robot actually has a full 3D camera in its head, so it can perceive its environment, review, collision avoidance, while doing manipulation.
Telepresence.
So that's a good question. It depends on how you define telepresence. The robot, you could have the capability to log into the robot and stream the data remotely and then actuate the robot in the remote, but are you going to have a screen on the front of the robot? No, this robot doesn't have that screen on it.
Did you say it's using a LiDAR or a camera to sense the environment?
So the question was, does it use, I said that it had a camera or a LiDAR to sense the environment. So the robot actually has two main, I guess, vision sensors. One in the head, which is a 3D camera, RGBD camera, like a Kinect type camera. And then in the base, it has a planar laser scanner that basically can see 4 to 6 meters out at a 180-degree field of view.
Can it be used outdoors?
No, it cannot be used outdoors. The camera technology, the Kinect, and the laser technology are both based on IR, and the sun is a very bright IR emitter, and the technology is not rated for outdoor. But there are sensors that can do it, so eventually you could possibly see it being outdoors.
Okay, let's go.
I'm still coming up. I actually removed the battery.
How long does the battery last? The battery lasts anywhere between 3 to 5 hours at continuous full-out use, or if it's in idle, it can last between 10 and 18 hours, depending on how you're just sitting there doing nothing, and it can last all day.
Compared to our tier 2 arm.
Yeah, compared to the Tier 2 arm. So kinematically, the arms are very similar. It has the same joint configuration, which is yaw, pitch, roll, yaw, pitch, roll. But the joint angles are different. The ranges are different. So the arm can actually go up higher than the Tier 2 arm. It actually has, even though the Tier 2 is a taller robot, this robot has a taller vertical reach. It can outreach a Tier 2 by about 3 inches. It can also reach the ground, which is something a Tier 2 can't do, and its base to arm ratio is better. So even though the Tier 2 arm is about 20 centimeters longer than this arm, there's actually a 7-inch difference, or I guess what is that, 14 centimeter difference between the ratio of the base to the arm. So this arm can actually reach deeper into a table than a Tier 2 can. But if you want to know more, we can talk more deeply about it.
How big a crew do you need to take Uber One out?
You need 2 people right now to take Uber One out. Uber One weighs about 160 pounds, and so we put the robot into a van, and then we just lift it up. It's a 2-person lift out of a van.
2-person job?
Yeah.
How many people did it take to deploy the PR2?
A lift gate, and
Just getting it in and out?
yeah, the Tier 2 weighed about 450 pounds, so it's a significantly bigger robot, yeah.
How does it charge?
How does it charge? So there's actually 2 methods for charging the robot. We have a external DC power brick that you can plug into the robot. We also have an autonomous docking station, so the robot robot can drive up onto its docking station and do continuous operations. The docking is just conductive. It basically has contacts that basically communicate with the dock and the robot to make sure that it's not a child licking the contacts. Well, you never know. Children are curious.
How can we order and what is the lead time?
Okay, how can you order and what is the lead time? We are getting ready to take orders. The lead time is about 9 months because we're going to do a production run. The entire robot's been designed for production quantities, and it just takes that long to do injection molding and get all the parts order and get the motors off the boat from China and things like that.
So it's a big price drop from the PR2 to this. What was your biggest cost savings in designing this one?
Okay, the question was what are the things that reduce the cost from this to the PR2? It's a really complex question actually, because the PR2 was designed 5 years ago, so there's some things that have greatly changed in the time since the PR2 was designed. One of the things to take note of is that the sensor that we use, it's like RGBD's camera, wasn't available 5 years ago, and so the sensor suite that's in the head of the PR2 cost $10,000. And so that alone is one of the reasons why the PR2 is so expensive. But the battery system in the PR2, since the PR2 had 2 full servers that didn't run in like a low power mode ever, they were just constantly running. The battery system with the PR2 was like 1.2 kilowatts, and it could run for 2 hours. So the servers were really burning through it, and that battery system cost more than the entire BOM of this robot. And then also the servers are very expensive. They were custom-made servers. Each server had its 4 quad-core processors, i7 quad-core processors. If you know the i7 when it came out like a year or 2 ago, so they had some first-gen i7 processors in the PR2, so those servers were very, very expensive. And then the other thing about the PR2 is when it was designed, it was only designed to really, the thought was, well, we're only going to make 5 of them. And then suddenly we're making 10 of them, and then next thing we know, we made 50 of them. And the robot was never actually designed for production. And so there's a lot of things that you do differently when you aim towards production with any piece of hardware. So there's a lot of things that, when you add all of that up, and then some of the engineering that we actually did to make the robot cost effective, because there is a lot of engineering work in here that we did, it all ends up being as cheap as we were able to make it today. What's the reliability? So that's something that we're trying to test out right now. We're doing extensive life testing on the robot, and we don't have any hard numbers yet that we want to talk about, but we'll see.
Could you give an overview of the types of computers in here? I imagine you have a big central one, lots of subsystems.
So the architecture of the robot is a single main computer in the back of the robot. It's actually attached to the torso of the robot, and then that's an i5 processor with like 8 gigs of RAM. And then all the motor controllers have just ARM microprocessors that run the control loop, and they're distributed throughout the robot. But there's no other large processing other than the computer of the robot. I just wanted to make sure. Any other questions?
So how hard will it be to repair, and will people be able to repair them?
Okay, the question is how hard will it be to repair? So we did a lot of things to make it very easy to repair. In fact, you can actually take the batteries out of this robot after removing 4 screws, actually 8 screws, and replace them. The robot was really meant to be easily repaired. We actually, before this, built a robot that was a lot harder to repair, and after having the opportunity, I might say, to work on that platform, we learned our lesson about making things that are difficult to repair. Dave?
Yeah, so we get to see what the inside looks like.
When do you get to see what the insides look like? When all of our patents are finally filed.
Well, I'm thinking if you were a company, you were buying this and you were depending on your production, they might want to have no replacement areas available in case something fails. So I was wondering, when you talk about the probability of somebody, what kind of fear on site would be overview?
That depends. That depends on training and, so it depends on what the service that they need to do. Some of it can be done easily on site. Others we probably would want them to do just because it probably involves a cable harness. And once you get a cable harness involved, I mean, basically you're running like a cable harness down this entire arm, and that kind of assembly work or repair work is very complex. You want to be done by a trained individual. But a lot of the other parts of the robot can be easily repaired by an untrained robot technician.
What about safety?
Safety, if you want to get to an arm wrestle, I think you'll win. So the inertia of the arm is relatively low. So that's one of the first things that you should be asking when you're talking about safety is the mass of the swinging mass of the arm and how fast it's moving. The next thing is pinch points. If you put your hand in here, yeah, if you're not careful with this robot, you might get hurt if you grab it in a certain way, but most of it, we've tried to accommodate that. Like right here, you can see that we've actually made it so that there's a pretty large gap here for fingers, so it'd be hard to get pinched. I would say that in general, no robot is 100% safe. I think that it's very hard to prove that. Because a lot of times it's depending on software, but we try to make the robot as safe as possible. And if you're a grown adult, the chance of you getting hurt by this is very, very low. I would say that maybe a small child who doesn't know what they're doing, like comes running up to the robot, possibly they could get hurt, but that's what emergency stops are for, and things like that. I think that it's always a bold claim when someone says that something's 100% safe. I mean, your car isn't 100% safe. You can slam your hand in the door of your car. You can slam your hand in the trunk. You can do all sorts of things that can't hurt you, and you use those objects every day, so the robot should be better. What's our wireless emergency stop? We don't have one. We actually have a dead man on our joystick. We do not have like an ISO-rated emergency stop on the wireless emergency stop. We just have a physical emergency stop on the back of the robot. Any other questions? Yeah.
In line with all the other robots that you're talking about in the presentation, is this given any indication that it wants to take over?
Has the robot...
Anything like in the log, hidden in the log files, or
The question was, has the robot given any indication that it wants to take over the world? Yes, it has. All robots have. When it first came into the office, the sheet metal came out of the box and said, "Ha ha! Now I've got you." So, any other questions? Alright, well, Mike's still over the software, but if you have any other questions, I'm willing to answer them. Even the absurd. There we go.
Going back to your history, one of my favorite robots was on your Johnny 5.
Oh, yeah.
Is there a reason why you're on Johnny 5?
I love Johnny 5. I just didn't want to bring Johnny 5 up because it's a soul-crushing robot if you're a roboticist.
Yeah.
I mean, any robot that comes alive and is like, no, this is simple, you just feel like, oh, well, crap, they're all right here. Any other questions?
Is your software going to be open source?
So the question was, is our software going to be open source? So we're going to provide an open source development kit that is based on ROS, and we're going to be releasing a simulator soon in Gazebo. We hope to do that in the next month or two. Gazebo is rapidly changing right now because of the virtual robotics challenge is being held by DARPA, and so it's kind of hard to keep up with that development, but we will have a simulator so that people can look and prod the robot virtually before we actually have physical ones. next. Building the robots. I mean, to give everyone, I guess, a sense of what kind of company we are. So we started in January of this year. There's actually only 4 of us. So we started from a clean slate. We did the entire design ourselves and all the software design ourselves. So there's been a lot of sleepless nights, considering that there's only 4 of us. And so for us, looking forward, we're looking to raise our Series A very soon and produce these robots and start collaborating with businesses to do business automation.
What do you see are the common use cases?
So the common use cases and the things that we actually designed the robot for are 3 different verticals. So there's basically light manufacturing, so stocking shelves, picking up items, sorting items, doing part inspection. Robots are great for part inspection because they can take the data record, everything they do, including pictures. All of those kinds of things that you would imagine, doing things in biomedical where you're basically picking things up like vials and sorting them, things like that. Obviously, elder care is a very large, talked about market. It may not be the first market we go into, but the robot's designed to be able to reach things on the floor, which is a primary use case for elder care. And then finally, hospitality. So using the robot to deliver room service and basically inspect rooms. We actually did some need finding with the hotel, and I learned an interesting acronym. It's called EPG, Evidence of Prior Guest. So every person who goes to a hotel ever wants to believe that the hotel was actually built that day. Like painters were running out of the room before you walked in. And so if you find anything in your room that's dissatisfactory, that's like already a red mark. And so robots can be very good at inspecting a room, basically doing a visual diff of the room. It looks like Mike has the software up and running, so
Yeah.
So you've probably all seen our vids before, right? This is the viewer for Ross. Right now what you're seeing obviously is the robot moving around, and now I see why we're not seeing objects to the head. Once I get the head back down there, it's actually now picking out where that table is and where that cube is, so that I can go out and grab that. So this is actually using a package called Move It, which is fairly new and does collision-free planning for the robot arm. So from there, I'm going to stop updating those continuously and switch it over and have it pick something up. So you see it updated there, it's all the object, it's going to come out, it's going to pick that up, and it's just going to move it to the opposite side of its visual frame right now. So just a simple demo showing sort of this whole system coming together. And so if I get moving that, it's actually doing everything online, all the planning, all of the actual object perception. And so this is one of those sort of things that will come out of the box. Users can go out and pick things up. For the Neo 2, this was actually like 3 years after they initially shipped, before you had that sort of capability available. When it first shipped, it had navigation, just drive around in a 3D world. And that was groundbreaking at that time, but this is even quite a bit further forward. Yeah. I haven't actually been listening to what you've been saying, so
well, that's fine.
I don't know what's been answered.
Every day at work. have to like bite.
Stop,
Okay.
swallow.
Yeah.
Does it have force feedback?
So the question is, does the robot have force feedback? So the arm is actually controlled by brushless DC motors, and we can measure the current going through the motor relatively accurately and get a good sense of force. And then you can do the forward kinematics, basically to project that force backwards and forwards through inverse and forward kinematics, and effectively compute the force at the end effector. It won't be as accurate as a force torque sensor, but it's a good approximation. And it's lower cost. Force torque sensor costs a lot of money. Yeah.
So that's what you were doing when you were moving the arms around, was just picking that up.
Oh, so
It was actually aiding you in moving it.
no. So the way the arm is actually being controlled is we actually have joint encoders on every joint and encoders also on the back shafts of the motors, so that we can get very accurate position and velocity estimates on the arm, and then we can do basically forward kinematics through the arm to basically get to a goal position.
What objects will it recognize and manipulate automatically?
So right now we haven't spent much time on object perception because it's a like actual research field. You can basically what you can do is you can do cluster planning or clustering. So you like if you don't know what this object is, you can identify unique or individual objects as clusters, and then try to pick up the object at the centroid. But if you cannot identify the object, say a cube or a cylinder, then you can get much better grasp plans for picking the object up. But I mean those kind of things are things that when you go into like doing it for a business or something like that, typically it's a semi-structured environment, and so you know that complete data set of objects that you're going to pick up, and then you're basically doing object detection based on that set instead of an infinite universe of objects. What's the payload of the arm? So the payload of the arm is 1.5 kilograms at full extension. Obviously, as you get closer and closer to the body, you can lift more and more because your arm configuration is like basically the torque that you need to lift that payload gets better and better.
When is it going to play Maxwell in chess?
When is it going to play Maxwell in chess? Soonish?
Yeah, at some point we will. Actually, we have run the chess code on here. I think you actually have Robo Business. It was running our B-roll in the background. It's a bit of a pain to set up, right? You got to drag all those pieces, the board, you got to set that up, and then you got to sit there and play a game with it. So it's not something we sort of carry around all that often. But that code actually, if you look in my GitHub repo where we did the chess code, you can actually go in there and there's settings for Maxwell or that other robot, which is actually this robot that we were working on all the way back in June, actually getting the chess code on there.
What is the power consumption for 4 hours?
So what is the power consumption? That's a hard question to ask because it depends on what you're doing.
Let me say that one again. So far in sort of our testing, driving around on level ground, we're sort of burning somewhere around 80 to 100 watts on average. Somewhere between 80 and 100 watts on average for the base, right? The arm is somewhere around 25 watts or so on average.
So for 4 hours.
And so you got about 600 watt hours of battery on board. So that's where, like, depending on what you're doing, it changes, right? Which is why we sort of quote a low battery number so that people don't come back and complain that, you know, it's not lasting until you 6. Your batteries are also going to degrade over as they age and whatnot, right? So on day 1, you may run a certain amount of time. After a year or 2, those batteries are going to be not as good as they were the first day.
Between 3 and 5 hours, something, or
Well, but the point is that it depends on what you're doing. If the robot is sitting like it is now, it could run for 10 hours. It just depends because when the motor, like Mike said, when the base is running, it uses on average 100 watts. So we have 600 watt hours. So if you run just the base at 100 watts, you can get about 6 hours. What?
There's also a computer.
Oh yeah, and the computer.
unlimited and sitting around, that's where your like really long runtime is going to be, because it's just the computer. So that's why I think you'll get better numbers than we're quoting generally, but that's all we're sort of saying. This is what you'll get.
We're extremely conservative.
I noticed it's a 7-degree freedom robotic arm. And then, what would you say the response time in terms of calculating the reverse kinematics of how would you rate the responsiveness or performance?
It depends on what the task is.
Just doing that.
Well, so what you're actually waiting for most of the time is the question was, what is the responsiveness of computing the forward kinematics or the inverse kinematics of the arm motion? But the thing that actually takes a lot of time there is, well, here, I'll just give you one away.
So there's a couple steps. When you want to grab something, the first thing is you're going to do inverse kinematics n times to get a solution where this is where my endpoint is based on actually picking up the object. Right now, that's actually using a numerical solver, so it's pretty slow. We just haven't generated the faster solver right now. There are other faster customized solvers, but it takes some work to set up. Once you've generated that, you're basically starting with joint angles here. You've got your joint angles at the end, and then you have to do interpolation between those, following your velocity acceleration limits, and making sure that you're collision free. And that is actually more of the time than the IK.
Yeah, inverse kinematics is very quick, like much quicker than you would even care to know.
How fast can it move and how good are the wheel encoders?
How fast can it move and how good are the joint encoders?
Wheel encoders.
Oh, the same thing. So the robot can drive at a velocity of 3/4 of a meter per second, and the wheel encoder. So the wheels have a backshaft encoder. It goes through a 10-to-1 gearbox and then a 2-to-1, I guess, transmission. So it's a 20-to-1.
It's really good.
It's really good, yeah. And then the encoder on the back is like a 14-bit.
Yeah, so you have sub-millimeter precision on the wheels. You're going to slip more than your encoders. But you can fuse the IMU into it.
It's really good, but I figured I'd give you more sense. Yeah, all the way back there. Yeah, I can answer now. So the question is, how is the arm staying up? So right now we're using active gravity compensation. So we use the position of the arm to compute the amount of torque we need in any position to counteract gravity. So basically we're doing forward or inverse kinematics calculation and the inertia matrix of the arm to compute the amount of torque we need to put into motors to keep it floating. And so you can see that the arm is completely back drivable, so I can move it around like this, and it's free floating, and it is always counteracting gravity. Now the thing is that since we are using active gravity compensation, when we hit the run stop, like I do now, the arm slowly falls, and we did that so that the robot didn't just like drop its arm out of the sky and slam into itself or the ground. We do that through creating kind of a viscous brake. So we use a relay and a resistor. Yes, Derek? I'm looking at my electrical engineer friend over there to create a kind of an active brake for the robot. Just so you guys know, I'm a mechanical engineer. Yeah. So and here's the thing on that.
Yeah. So straight out with no payload is about 12 watts on average, which is less power. Like basically, you have this trade-off. So the Meter 2 was counterbalanced, so the arm weighs 80 pounds versus the 30 or so that this arm is. which means you use more power when you're actually moving around. So you get a sort of trade-off. If you're going to be moving a lot, you're actually better off doing the active gravity compensation and using less power when you're moving.
What watts over how much time?
Negative.
What watts over how much time?
So, yeah, I mean, so 12 watts continuously, so if you run for an hour, it's 12 watt hours, right? So out of your 600 watt hours for the battery, that's a very small portion, right? Your computer's using 4 times what that gravity compensation is using.
All right, well, thank you very much. If you guys want to come up and take pictures with the robot, and thanks.
Thank you. Thanks, everybody, for coming to this meeting. Our next meeting will be in January. We have no meeting in December. So I just want to remind you of that. No meeting in December. It's the middle of the holidays. We're going to show up anytime. So thank you very much and have a great evening.